I consider science to be the study of the natural world.
Science is really a very public, open endeavor.
I think everyone, just to function in this world, needs to know some science. You need to understand what science is and have some sense of when you have good science and when you have bad science.
So what is science? To some, it might be technology or some kind of result. To others, it's a process or a method. And to some, it might be something a little more mysterious. Well, today we're going to talk about science. We'll discuss what science is and what it's all about. And we're also going to hear from some real working scientists who will share in their own words the nature of science.
John Armstrong. I am currently a professor of physics at Weber State University.
Okay, so what is science?
I actually have two answers to that. The first one is my stock answer, that science is a way of knowing. It's a way of, through observation and experiment, determining whether or not ideas that we have about the universe are valid. Okay, that's the one thing. But I also think of science as a culture. It's a way of being, a way of looking at the universe, right? The scientist believes, and that's an important word here, the scientist believes that the universe is understandable and that the universe is knowable. And we don't know if that's true or not. And so when somebody talks about science-based reasoning or faith-based exploration, I mean, science is faith-based, right? You believe that the human mind can comprehend the universe.
Scientists use words to talk about what they do, and sometimes those words are a little misunderstood. One commonly misunderstood word is law. In everyday language, a law is something that cannot be broken, or at least it shouldn't be broken. Our governments make laws to protect people. If you break a law, you might wind up in jail. Scientific laws are different. Scientific laws are used to describe something that can be consistently observed. For example, the law of gravity. It says massive objects attract one another. That's another way of saying stuff falls down. The law of gravity does not explain why gravity works. It only describes what we observe. Here's another example. Let's say you're an ornithologist. Now, that's a scientist who studies birds. You travel all over the world, and you're counting birds, describing birds, and chasing birds. After a lot of travel, you realize that every swan you've ever seen is white. Based on this observational evidence, you establish the law of swans. And it says, all swans are white. You publish a paper, you go to conferences, and you lecture at university. You continue your work, and everything is great. Until your expedition to Australia. Huh, black swans. Wait a minute, black swans? These birds just broke your scientific law. What are you going to do? We could A, ignore the swans, just pretend they don't exist. B, we could arrest the swans because, they broke that scientific law. Or C, incorporate the new observation into your law.
Science is really a very public, open endeavor. People, not only just throughout the country, but from all nations, get together at conferences. And they try to push ideas to their limits and test them and see where they might be wrong. And the glory comes not in maintaining the status quo, but in overcoming it and overturning it.
The framework of science lets us update our old ideas in light of new evidence. And this is what makes science so cool. Our understanding improves as new information becomes available. Now, scientists don't just look at stuff, they also figure stuff out. Once a scientist observes something, the next question is why?
You may notice something and you hypothesize why that might be, and you set up an experiment to test it. Oftentimes, you actually disprove your hypothesis, which still gives you more information to go on. And so if it disproves it but doesn't answer your question, you'll just have to come up with a new hypothesis.
Scientists don't always follow one single recipe when they're working. So compare Dr. Skopek, the biologist we just heard from, to Dr. Eaton, a paleontologist.
In paleontology, you don't even know what you're looking for. Sometimes you're just out there and you have an object you find, and then you have to explain what that object is doing there. So the object comes first, and then the hypothesis is generated. And then hopefully you devise ways of testing it. Hopefully we'll find more of those. Other people will find it. Then our assumptions about what it's doing there and why it's there will be tested and make sense. Or it won't, and back to the drawing board.
Now, although scientists work in different ways, the important thing to remember is that all science depends on evidence. If observations or experiments disagree with a hypothesis, that idea needs to be modified to account for the evidence. If observations and experiments support a hypothesis, that idea is strengthened. This is how scientific theories are built.
The scientific theory is really the endpoint of the investigation into nature. It is a set of ideas that are comprehensive in their explanation. They can explain many interrelated facts. They can make successful predictions that have been tested. They have wide applicability. They are the ultimate. So you have Einstein's general theory of relativity. You have Darwin's theory of evolution. You have the theory of the Big Bang. All of these things have been tested over and over and over again, and they've passed every test that they've come on. And there's a common idea that, you don't want to see your theory proved wrong. Nobody wants to see their theory proved wrong, but science lives by proving theories wrong. That's how it's self-correcting.
When I talk about this with my classes, I try to emphasize that a theory is something we can use to predict other things. So we can use the theory of evolution to predict how organisms might be related to one another using their DNA. So we can not only predict how two organisms might be related, but then we can use the DNA from those two organisms and see that they really are related the way we expect.
There could be no better evidence for a theory than there is for evolution. Far better, for instance, and far better explained than gravity. We have an enormous fossil record with museums full of millions and millions of specimens for which an argument was made about the relationship and the overall evolution of organisms. And then more recently, a completely different branch of science without the slightest interest whatsoever in fossils. The geneticists have looked at modern DNA, and we have two completely separate areas of science agreeing entirely.
Now that we have some idea of what science is, let's talk with some scientists one-on-one. Dr. Michelle Skopek is a professor in the Department of Zoology at Weber State University. She studies wood rats.
I've been studying wood rats for the past 5 years. They're these small rodents that are herbivores, so they're eating plants only. What's really interesting about wood rats is that they build these stick middens, so sort of like beaver dams but on land, and they cache all their food in them. So we kind of know exactly what they eat because they cache exactly what they eat. Anthropologists actually really like to study wood rats because you can recreate ancient environments based on what they've cached. So there's middens out there that are 50,000 years old. And so you can sort of see what was in the environment 50,000 years ago.
So why do you do science? What's in it for you?
For me, it's just an innate desire. Like, I can't imagine not wanting to know how something works. And so for some people, that means they want to know how their car works. And for some people, it's how their computer works. And for me, it's how my body and other animals' bodies work. I mean, without science, it would be a pretty dull world, just like without art, it would be a pretty dull world.
My name is Michelle Zulinski. I work in the microbiology department at Weber State University.
Dr. Zwolinski studies extreme halophiles in the Great Salt Lake.
Regular halophiles and extreme halophiles.
Oh, okay. What is a halophile?
A halophile is any organism that can live in very salty conditions. Most of the time, these are what we call microorganisms. So they're either bacteria, archaea, and some eukaryotic organisms, so types of algae that like to live in the lake.
So what are you trying to learn from these little guys?
We want to find out things about their ecology. We're studying the phosphate cycle. Phosphate or phosphorus is an important nutrient for organisms, and nobody's looked at how organisms in the Great Salt Lake get phosphate. We look at organisms that decompose the molecule chitin, and all those brine shrimp that are in the lake are made mostly of chitin, this very complicated, tough molecule, and there are microorganisms that can break it down.
Okay, but why should we care? Why should we study microorganisms?
One of the things is sort of a pure discovery, because we don't know what 95% of the microorganisms on this planet are. And then the other things, because we don't understand the diversity of these organisms, we don't know what they can do. We find microorganisms from soil and from extreme environments all the time that produce interesting molecules. Maybe we could use that ability to develop a new pesticide, or we might be able to use for biofuels or degradation or even medicines. Most of the bacteria and microorganisms on this planet don't do us any harm, and in fact we couldn't live without them. So I think that it's important to understand those other beings on the planet.
All right, we're going to step away from the Earth for a minute with astrophysicist Dr. Brad Carroll.
I'm chair of the physics department, and I am a professor of physics at Weber State.
When did you become interested in astronomy?
Yeah, since a child, I've always been interested in stars. I remember getting my first telescope from my grandfather and looking through it, and you could see, all these stars that you couldn't see with your naked eye. And that told me that there was a lot out there that I couldn't see. And I remember, actually I was a math major as an undergraduate, and finally decided that I wanted to use this for something. And so I took a physics course. And I remember the physics course was talking about Kepler's laws of motion of the planets. And they were able to derive that mathematically from Newton's laws of motion. And I was just amazed. This means that things in the universe have reasons. That it's just not just a bunch of random rules out there. There's a coherent structure to the universe. And I wanted to know what that was. And I still do.
Brad, you seem to have a lot of fun doing what you do. Why is science fun?
Gosh, that's such an interesting question. I mean, you don't ask why it's fun to wake up to a fresh scene of fallen snow, or why it's fun to take a hike and find a waterfall. You don't ask why those things are fun. They just naturally are. It's like I see miracles everywhere I look, and everything I see is informed by science, so I can take delight in very ordinary, mundane things. I can appreciate how things work. I've heard people say that if you know how a rainbow works, that takes all the beauty out of it. To me, knowing how a rainbow works has always enhanced the beauty, because I can really appreciate all the things that are going on in those little droplets of water. It doesn't have to be anything spectacular and grand. It's that everything you see is a richer experience because of knowing the science that's going on.
So why should we study things in space?
Suppose you were just born in a room that had no windows, and all your life you were raised in this room, you read books in the room and so on. And then someday somebody put a window in, but the shade was pulled down. Would you want to raise the shade and see what was outside? Of course you would. Anybody would. And that's what astrophysics does. We're taking a look not out through our bedroom window or a window in a room, but we're using telescopes as windows to peer deep back into the universe.
All right, let me tell you a story. Just over a century ago, Orville and Wilbur Wright made the first successful powered flight at Kitty Hawk. And before this, people would use gliders to fly around. But people started ballooning even earlier, as early as the 3rd century, and we still use balloons today. This Kongming lantern is one of the oldest balloon designs. As the flame heats the air inside the balloon, the density of the air decreases and the balloon begins to rise. In the 3rd century, these were used for military signaling. Today, they're used in Chinese, Thai, and Taiwanese festivals. For more lift and a little less fire hazard, today's scientist uses a helium balloon.
We have a high-altitude ballooning program here. We've called ours HARBOR. It stands for High Altitude Reconnaissance Balloon for Outreach and Research. HARBOR is designed to get people excited about science and get people excited about the prospect of traveling into space, because it's the one way I know of to send things directly to near space without having to talk to a large government agency to do it. In fact, we like to say near space is 60 minutes away, because that's about the time it takes for our helium balloons to get up to 100,000 feet. The students build everything. They do everything. They've built all the electronics. They've built all the payload modules. They've put everything together. And so they're the ones who are in charge of whether we succeed or not. To fly the balloon, you need people with advanced skills in reconnoitering or, GPS tracking. You need people with ham radio licenses. You need all these people who know all this stuff, but you also need a guy to hang on to the rope. And so we can always use more people to hang on to the rope, and that's how you get into it. And then next thing you know, you're a ham license operator, and you're actually running the base station that's helping track the balloon. In our very first launch, we underfilled the balloon by quite a bit. And so it went up about 12 feet, and then it came back down. And one of our students ran out and caught it like a football player. We hauled it back, we filled it up with more helium, and then that same day, that same balloon went to 80,000 feet. You'd like to say that we all really know what we're doing when we do this, but there's so many variables and there's so many things that can happen. It's real life. It's a real life experiment.
Well, why should we fly balloons or study microbes or look at the stars? What does science do for us?
2,000 years ago, when some guy pulled a lodestone out of the ground, for those of you who don't know, a lodestone is basically a naturally magnetic rock. They didn't look at that and say, I have got to make a cell phone out of this thing. If I could just figure out how this thing works, I could have a cell phone, right? They didn't say that. They said, this is a very weird thing that appears to attract metallic objects. What's going on here? Now, electricity and magnetism, as we understand it, drives every single technological advance on the planet, right? Nobody could have foreseen that. Science gives you power. If I could get people to understand anything about science, it's that it belongs to you. That it gives you a power to know things that is independent of anybody else on the planet. You can just figure stuff out.
Science is for everyone. If you like to learn new things and figure stuff out, you can get involved. Imagine the thrill of discovery that Darwin felt as he explored the Galapagos, or how the men and women of the Voyager missions felt as they received the first ever close-up pictures of Neptune. These are everyday people who expressed their curiosity and dared to ask why.
Hello from the children of planet Earth.
Hola y saludos a todos. धरती के वासियों की ओर से नमस्कार. नमस्कार. विश्व शांति हो.
I think the main legacy of Voyager is to, in fact, have opened up our solar system in a way which was not possible before the space age. It revealed all of our neighbors in the solar system, and it showed us how much there was to learn and how diverse the bodies are that share the solar system with our own planet Earth.